Okay, so the focus today is going to be working with limits that are indeterminate. So if you remember, we've talked about this in this class before, where if we have certain limits where we have 0 over 0, we basically don't know what that could be. Okay, so remember, what we care about is if I have if I'm trying to evaluate a limit as x approaches a number, I don't care if that function is undefined at the number. I want to know what happens as I really get close to that number. What happens to the function when I get close to that number? So if you remember, we dealt with certain cases, for example, sine theta over theta, where limit as theta goes to 0. That's indeterminate because it was 0 over 0, and then we discovered that that ends up equaling to 1. So we're going to focus on a bunch of limits today where we're going to have indeterminate form. So we'll define what are the cases where we'll have limits that are indeterminate, and then what rule are we going to use to help us figure out these indeterminate forms, and that's going to be L'Hopital's rule. So please don't call this L'Hospital, because that's probably one of my biggest pet peeves. It's L'Hopital. So let's pronounce this mathematician's name correctly. So let's start by defining what indeterminate forms are. So this is kind of, we're going to start off with the first set of indeterminate forms, and then we are going to talk about a bunch of other ones. So these all relate to limits. So if we have a limit of the form, let's say limit as x approaches a of f of x over g of x. So none of this should look new to us. We've dealt with limits, and this is specifically taking a ratio. And what we notice is, and if f of x goes to 0 and g of x goes to 0 as x approaches a. So basically what are we noticing? As x gets close to a, f gets close to 0 and g gets close to 0. So basically I have 0 divided by 0. So this is the first type of indeterminate form that we have. So we would say then this limit may or may not exist. And is called indeterminate form of type 0 divided by 0. So basically, why is this indeterminate? Because when we have something that's 0 over 0, we're saying, look, this limit may exist or it may not. So that's why it's kind of like indeterminate. We don't know yet. So we need to figure this out. So before we go any further, let's talk about, so the only type of indeterminate form we know right now is if you get 0 over 0. So there are two more types, or there's one more type I want to talk about, and then we'll introduce ourselves to L'Hopital's rule, and then we'll put that to use. So we could also say same thing for this limit if f of x approaches infinity or even negative infinity. So I don't care if f of x goes to infinity or negative infinity, as long as it goes to some type of infinity. And same thing with g of x. G of x also goes to infinity or negative infinity. Now, you could have any combination of these. It could be infinity over negative infinity, or infinity over infinity, negative infinity over negative infinity, or negative infinity over infinity. It doesn't matter at any order, okay? So as long as I'm dividing any kind of infinity by another infinity, then, so we could say as x approaches a, then this is called indeterminate form of type infinity over infinity. So if you ever have any infinity divided by infinity, this is still indeterminate. So we're saying, well, what does this become? This could take on any value. So there are ways that we will deal with this, okay? So now, when we have indeterminate of type 0 over 0 or infinity over infinity, the good news is we have a nice and easy way, or a convenient way of checking to see or to see if this limit exists or not. And that method is L'Hopital's rule. So let's define what L'Hopital's rule is, and then we'll put this to use. Okay, so L'Hopital's rule says the following. Suppose f and g are differentiable, and g prime of x does not equal to 0 near a. So suppose that if you have the limit as x approaches a of f of x equals to 0, and the limit as x approaches a of g of x equals to 0, or that we have the limit as x approaches a of f of x equals to plus or minus infinity, one of these two, and limit as x approaches a of g of x equals to plus or minus infinity. So basically what we're saying is, look, you're trying to evaluate a limit where it's f over g. Okay, so what this is saying is, if you have 0 over 0 or any kind of infinity over infinity, then we could use L'Hopital's rule. So here's what L'Hopital's rule says. Then the limit as x approaches a of f of x divided by g of x, that's equivalent to the limit as x approaches a of f prime of x divided by g prime of x. So basically L'Hopital's rule, and the proof of this is in the book. So if you'd like to look at the proof, you could. I just want to kind of put this to use and for us to move on and evaluate these indeterminate forms. But L'Hopital's rule says, look, as long as you have 0 over 0 or infinity over infinity, if you just grab f and take its derivative, and you grab g and take its derivative, this limit will be equivalent to that limit. But remember, this only applies to indeterminate forms. So, and one other thing I want to point out is, a common mistake people make is they think, oh, you're finding the derivative of the whole thing and you're using the quotient rule. That's not what L'Hopital's rule is saying. L'Hopital's rule is saying is, if you have indeterminate form, what you do is you just take the derivative of f separately, and then you take the derivative of g separately, and then this ratio, the limit as x approaches a, will be the same as that ratio. Which basically, what we're trying to figure out is why this works the way it does. And just to kind of give you an idea is, see, if this is indeterminate, the question is, as this approaches 0 and as this approaches 0, are they approaching 0 at the same rate? And if they are approaching 0 at the same rate, then their derivative should also approach 0 at that same rate. So what this will happen is, this will kind of help us see what is that rate. Is it 5, 10, 1, or e, or whatever it could be, okay? So L'Hopital's basically, just quickly, once again, to summarize, says if you have indeterminate form of type 0 over 0, so remember, I want to make certain here that this is only for type 0 over 0 or infinity over infinity. Okay, so of course we need a fraction. So this limit is equivalent to the same limit, except you find the derivative of f and g separately. So if you could evaluate this, whatever this is, it's the same thing as that. Okay, so for indeterminate forms, L'Hopital's rule comes in pretty handy. So let's look at our first example where we'll put L'Hopital's rule to use. And of course, the first example is going to be one of my favorites. Limit as x approaches 0 of sine x over x. So if you think about it, if we were just to use the substitution property here to see if I could evaluate this limit, and of course I can't, but if I plug in 0 For sine, what do I have? I get sine of 0 over 0. And what's sine of 0? That's 0 over 0. So what do I notice? That this is indeterminate of type 0 over 0. So let's use L'Hopital's. L'Hopital's basically guarantees the following. Says the limit as x approaches 0 of sine x over x. Since this is indeterminate of type 0 over 0, this is equivalent to the limit as x approaches 0. And now let's find the derivative of each separately. So what's the derivative of sine, which is cosine of x, divided by the derivative of x, which the derivative of x is 1. And look at how nice this looks. Now I notice I could use direct substitution because my denominator is no longer zeroing out. So what happens here is if I use direct substitution, I just get cosine of 0 over 1, which cosine of 0 is 1, and that gives me 1. And so notice how here's another way where we show that the limit as x approaches 0 of sine x over x is 1. If you remember at the beginning of the year, we made a table and then we said, okay, so through a table that this is 1. And then later on, we showed through linearization that as x is close to 0, sine x and x are roughly the same thing, which they end up canceling each other out. You get 1. And then here's another way where we use the indeterminate type 0 over 0. So we use L'Hopital's, and we found the derivative and equal to 1. One other comment I want to make. If I used L'Hopital's from here to here, and I saw that this was still indeterminate, like let's say 0 over 0, then I could use L'Hopital's again. So you could use L'Hopital's multiple times over and over and over, as long as you have the correct type of indeterminate form, whether it's 0 over 0 or infinity over infinity. Okay, so let's look at one more example. And in fact, I'd recommend that for this next example, you pause the video and then you do it yourself, and then press play and see if you got this yourself. So the limit as x approaches 0 of e to the x divided by x squared. So if you think about it, as x goes to infinity, e to the x goes, it's an exponential function, so that's infinity over, and x squared, if I plug in infinity, I get infinity. So what is this? Indeterminate type of infinity over infinity. So once again, I don't know what infinity over infinity is. So once again, though, I could use L'Hopital's. So if I come down, I could say limit as x approaches infinity of e to the x over x squared. This becomes, let's find the derivatives, limit as x approaches infinity of e to the x over 2x. And so what do I notice here? As x goes to infinity, e to the x goes to infinity, divided by 2x also goes to infinity. So sure enough, notice how this is still indeterminate type of infinity over infinity. So what could I do to this? I could apply L'Hopital's again. So if I apply L'Hopital's, I get the limit as x approaches infinity. The derivative of e to the x is e to the x over 2 to the 2x becomes just 2. So now look at what happens here. As x goes to infinity, e to the x goes to infinity divided by 2. And notice how this is no longer indeterminate. So what's infinity divided by 2? I mean, that's just infinity. So what are we saying? In other words, this limit does not exist. So we just did two examples. The first example, it was indeterminate, but the limit existed. In the second example, it was indeterminate, and then later on we found out that actually this is a non-existent limit. Okay, so now we have other types of indeterminates. So let's move on to the other types. We could also have indeterminate products. And so what are the cases where I get indeterminate products? So let's define this. We could say for the limit as x approaches a of f of x times g of x, if the limit as x approaches a of f of x equals to 0, and the limit as x approaches a of g of x is plus or minus infinity, this is called indeterminate form of type 0 times infinity. So once again, you might say, wait a minute, shouldn't 0 times infinity be 0? Because usually we've always learned, hey, 0 times anything is always 0. But let's be careful. This is the limit notation. So what are we saying? As x approaches a, f of x approaches 0. And then what is this saying? As x approaches a, g of x approaches infinity. So we're not saying that f of x is 0. We're saying that f of x is getting closer and closer to 0. And then we're saying g of x is getting larger and larger and larger. So why is this indeterminate? Because the question between these two is, which one wins? See, if this approaches 0 much faster than this guy is getting bigger, so then the 0 is going to overpower this, we're going to get 0. Or if this guy is increasing much, much faster than this guy's approaching 0, then this infinity won't allow the 0 to ever get to 0, which means this might level off to a number, or it might infinity might overpower it by so much, whereas 0 times infinity ends up being infinity, and so on. So the reason why this is indeterminate, or anytime you have a limit, if you have two possible outcomes, it's automatically indeterminate. So the question is, what are the possible outcomes? And so in this case, we have so many possible outcomes. So now, here's the other problem. I don't like this, because if I want to use L'Hopital's rule, if you remember, L'Hopital's only applies to what? 0 over 0 or infinity over infinity. So L'Hopital's, I can't use it on 0 times infinity, or I can't use it on a product of two functions. So what I need to do is, to be able to use L'Hopital's, I need to somehow come up with a fraction. Okay, so here's how we're, and this part's actually really, really cool, the way it works. So this is how we're going to manipulate something like this so that we could use L'Hopital's. So what we can say is, look, we can write the limit, or the product, f times g as what? As the same thing as the following. F times g is equivalent to f divided by 1 over g. So look at what's happening here. Isn't this, I mean, if you look at this, hopefully this verifies, because f divided by 1 over g, that's basically f times g. Okay, now why do I prefer this notation? Because look at what's happening. As x approaches a, what does f approach? F approaches 0. So notice how this f on top is 0 divided by, and as x approaches g, or x approaches a, what does g approach? G approaches plus or minus infinity. Now look, what's 1 over infinity? And if you remember, we did that earlier on in the semester. 1 divided by infinity is actually 0. So look at what I just did. Just by rewriting this product as that fraction, I created indeterminate type of 0 over 0, which then what does that mean? So we can use L'Hopital's. And that's kind of like the important idea here, okay? And by the way, if you're wondering, could I have written it as g over 1 over f? Absolutely, you could have. And I think that would have given you infinity over infinity. And remember, L'Hopital's, all we really care about is, as long as it's 0 over 0 or infinity over infinity, we can put that to use, okay? So let's look at our third example. And this one says, find the limit as x approaches 0 from the right side of x times ln of x. Now, what do I know here? For this guy, what we have is, as you approach 0 from the right side, what does x approach? X approaches 0 times, what happens to ln of x as x approaches 0 from the right side? It goes down to negative infinity. So it's 0 times negative infinity, which notice how this is an indeterminate product. So to be able to use L'Hopital's, I need to first write this as a fraction. So what my options are this. Either grab the ln of x and write it as 1 over ln of x. And I don't like that, because usually when I have ln of x, I'd rather leave that in the numerator, because right away I know that the derivative of ln of x is 1 over x. So that's an easy derivative to find. So if it were up to me to write these as one of these as a fraction, I would grab x and write it as 1 over x. So what we could do is we could say x ln of x is equivalent to the limit as x approaches 0 from the right side of ln of x divided by 1 over x. Okay, so now let's verify that this is indeterminate, so I could use L'Hopital. As x approaches 0 from the right side, ln of x goes to negative infinity, divided by, as x approaches 0 from the right side, 1 over a very, very, very small positive number is infinity. So sure enough, infinity over infinity, I don't care if there's a negative or not, that doesn't matter for me. It means I could use L'Hopital's. So let's apply L'Hopital's. Using L'Hopital's rule, we get limit as x approaches 0 from the right side. The derivative of ln of x is 1 over x over the derivative of 1 over x is just negative 1 over x quantity squared. And then I could simplify this, and hopefully I can get a solution out of this. So as x approaches 0 from the right side, 1 over x divided by negative 1 over x squared, that just becomes 1 over x times negative x squared, which ends up being negative x. And if that's negative x, then I could just simply say, as x approaches 0, negative x goes to 0. So basically in this one, if you think about it, this guy approached 0 quicker than that guy approached negative infinity, which means then it ended up basically giving me a 0. Okay? So moving on to a few more other indeterminates. So we also have indeterminate differences and indeterminate powers. So as far as the indeterminate differences go, let's talk about this, and then we'll talk about indeterminate powers, which those are pretty much the more important ones, or the ones that we'll probably deal with more often. So what we're saying for the difference is the following. For the limit as x approaches a of f of x minus g of x, if I have this limit, what we could say is if the limit as x approaches a of f of x is infinity, and the limit as x approaches a of g of x is infinity, this is called indeterminate of type infinity minus infinity. So once again, we've talked about this before. Infinity minus infinity, you can't say that's 0 because infinity is not a number. What we're saying is this is getting really large, this is getting really large, but I don't know what the difference is. I mean, because if this is increasing faster than that, then the difference isn't 0. But if these guys are basically increasing at the same rate, then the difference could be 0 and so on, or the difference could be 2. So this is indeterminate because I don't know what infinity minus infinity is. So for this one, it's kind of a little more difficult to use L'Hopital's. So our goal for something like this would be to kind of maybe solve by factoring or get a common denominator. So for this one, we want to kind of simplify in different ways. So our goal here will be to write the difference as a quotient by using a common denominators. So basically, if I notice that f and g are two different rational functions, maybe I should get a common denominator, put them together, or rationalizing, or factoring. So for this one, there may be different ways where I could try to kind of force out a fraction from this. And sometimes I might not be able to force out a fraction. Like if I have something like this, limit as x approaches infinity of x cubed minus x squared, that's infinity minus infinity, and I can't force a fraction out of this. But what you notice is I could rewrite this as limit as x approaches infinity. If I could factor out an x squared, what do I get? I get x squared times x minus 1. And so what do I notice? As x goes to infinity, x squared goes to infinity, x minus 1 goes to infinity, and what do I know? Infinity times infinity is infinity. So there may be instances where you don't necessarily need to use L'Hopital's, or you could somehow manipulate it where you get it to be in terms of a fraction. Okay? So for the indeterminate differences, we'd have to manipulate it in a different way. It's not as straightforward as the indeterminate products, where we could kind of force it out as long as I have 0 times infinity. So the last type of indeterminate limits we're going to see are the indeterminate powers. Okay, so for the indeterminate powers, this is actually also very cool the way we're going to approach it, because you get something that looks like you can't simplify or work with or use L'Hopital's, but it's kind of like something happens and then wow, all of a sudden you're like, I could use L'Hopital's, and L'Hopital's is a nice way out of things. So here's what we could say. For the limit as x approaches a of f of x to the power of g of x, here's what we could say. So basically I have a function to the power of a function. The first type of indeterminate powers are the limit as x approaches a of f of x equals to 0, and the limit as x approaches a of g of x equals to 0. So this is actually of what type? Type 0 to the power of 0. So once again, what's 0 to the power of 0? I mean, remember, if we could come up with more than one possibility, then it's indeterminate. Well, I know that anything to the power of 0 is 1, or 0 to the power of anything is 0. So notice how this is indeterminate, because the question is, what is it? And sometimes it doesn't even necessarily have to be 0 or 1. It could be some other number. So anytime you have 0 to the power of 0 when you're trying to solve this limit, then that's indeterminate. So we'll kind of see in a minute how we would manipulate this to be able to use L'Hopital's. And then the other possible scenario is the limit as x approaches a of f of x equals to infinity, and the limit as x approaches a of g of x equals 0, which this is the type of infinity to the power of 0. So if I have infinity to the power of 0, I still don't know what that is. So once again, we would have to manipulate this exponential in a way where I could solve it using L'Hopital's. And then the last type would be the limit as x approaches a of f of x equals to 1, and the limit as x approaches a of g of x, which is plus or minus infinity. So this is of type 1 to the power of infinity. Okay, so the approach to this is, and let's talk about what the approach to this is, because here's the problem. To be able to write this as a fraction, I would somehow like to see if I could bring this down, okay? And hopefully you're already seeing what it is we need to do. So here's what the approach is like. So the approach to solving this, to solving these, are either by taking no, or we shouldn't say are either. The approach to solving these are by taking the logarithm, or let's be more specific, taking the natural log of the expression. So you're going to natural log it. Why do I want to natural log this? Because if I natural log this, then I could bring the g of x down. Okay, but remember, if I'm natural logging this, I'm kind of chaining this problem up. Okay, so just keep in mind that when I natural log this, why do I like it? Because when I bring the g of x down, then I get a g of x times ln of f of x, which then now I have a product. And the product I have hopefully will be indeterminate of 0 times infinity, which then I could use the whole trick about the products where you take, you write as a fraction, and then you could use L'Hopital's. But just keep in mind that when you take the ln of the expression, eventually you're going to have to undo this at the end, because I can't just leave it in terms of ln. So then we will undo this at the end by taking the exponential of e. Okay, so basically, the whole reason why we natural log this is so we could bring this down, write it as a product, and then we can, if I go back to um, the earlier stuff, to the indeterminate product, then I could write it like this and use this trick to use L'Hopital's. So that's the reason why we ln it. But remember, when we ln it, we have to undo it. Okay, so that's very, very important. So if we look at example 4, we'll do that example just where you'll see how this is in play. So what we could say is find the limit as x approaches 0 from the right side of 1 plus sine of 4x to the power of cotangent of x. So if you remember, cotangent of x at 0 had a vertical asymptote. So what we notice is we could say, look, notice the limit as x approaches 0 from the right side of 1 plus sine of 4 to the x to the cotangent x. As x approaches 0, sine of 4x goes to 0, and cotangent goes to infinity. So what we could say is the following. We could say this becomes 1 plus 0 to the power of infinity, which is 1 to the power of infinity. So this is indeterminate of type 1 to the power of infinity. So the trick we're going to use is by natural logging this guy. But what I always like to do, just so I don't forget about the natural log, here's what I do. I always say let y equal to the limit as x approaches 0 from the right side of 1 plus sine of 4x to the power of cotangent of x. So then what I'm going to do is, how do I, basically I want to ground this cotangent. How do I ground that cotangent? By natural logging both sides. Now, this is extra, but the reason why I'm putting this is because now what am I solving for? Our goal initially was to solve for y, because y was this limit. Now we're solving for ln of y. But once I know what ln of y equals, then I could get rid of that ln and initially find what, or ultimately find out what y is. So what happens is when I do this, I could say then this equals to what? I could say ln of y equals to, I could bring the cotangent down because of the properties of logarithms. It'll be what? Cotangent of x times ln of 1 plus sine of 4x. Now let's see what happens. As x goes to 0, cotangent goes to infinity, times, as x goes to 0, sine of 0 is 0, and I'm left with what? Ln of 1. And what is ln of 1? It's 0. So notice how it's infinity times 0, which is the indeterminate product. And see, we're good at this by now. I could rewrite this as a fraction, so I could use L'Hopital's. So here's what we could say. Ln of y equals to the limit as x approaches 0 from the right side. I could say, well, I could grab the cotangent. Remember, I want to leave the ln in the numerator because that's easy to find the derivative of. And cotangent is the same thing as what? 1 over tangent. So I could say this is the same thing as ln of 1 plus sine of 4x over tangent of x. Now let's see if this is actually indeterminate where I could use L'Hopital's. Remember, it has to be either 0 over 0 or infinity over infinity. So as x approaches 0, tangent of 0 is 0 over, as x approaches 0, we've already talked about this, sine of 0 is 0, so I'm left with ln of 1, which is 0. How nice is that? So look at what's happening here. I did all of this so that I could use L'Hopital's. So now what I could do is, using L'Hopital's, I would say the derivative of the top, so the limit as x approaches 0 from the right side, the derivative of ln of 1 plus sine 4x will be 1 over 1 plus sine of 4x times, don't forget the chain rule, 1 zeroes out, the derivative of sine is cosine 4x times the derivative of 4x, which is 4. Okay, and then I also have to find the derivative of tangent x, which is secant squared x. So let's simplify this and see what we get. And hopefully this will simplify where I don't need to use L'Hopital's again. So what do we have here? If I were to multiply this out, I get this equals to 4 cosine of 4x divided by 1 plus sine, oh, let me not forget the limit, that's important, limit as x approaches 0 from the right side. 1 plus sine of 4x divided by secant squared x. So let's see what happens here. If I plug in 0, what do I get? Cosine of 0 is 1, so it'll be 4 times 1 over sine of 0 is 0 plus 1 is 1 divided by secant squared. Well, secant is the reciprocal of cosine, so if cosine of 0 is 1, secant of 0 is also 1, so this becomes 1 squared. So how nice is that, actually? So what do we get? 4 as our answer. But here's the thing. Here's a common mistake you could make. You might say, oh, my answer is 4. I'm done. Let's move on. But remember, my answer is not 4 because what did I do here? I said ln of y equals to this limit, which this limit equals to 4. So what did we find? This implies ln of y equals to 4, which then, remember, ultimately, before I took the ln, my goal was to solve for y. So if ln of y equals to 4, this implies that y equals e to the 4. So what did I do? I undid the ln that I took. So actually, the answer is e to the 4th. So in other words, what we just did, all of this work, was what? The limit as x approaches 0 from the right side of 1 plus sine of 4x to the power of cotangent of x, that's e to the 4. That's what we did, right? Because if you remember, I initially called this, I said, let this equal to y, which is the same thing as this limit. So when I ln'd it, I was no longer finding y, I was finding what the ln of y was. And we found out that the ln of y, which is the limit of the ln of this guy, is 4. Then if the ln of y is 4, then y is e to the 4th, which y is the same thing as this limit. And so there you have it. Okay, so these indeterminate forms, as far as the AP exam goes, not that I teach for the AP exam, I honestly care more about the calculus than just the AP exam. On the AP exam, you're not expected to know L'Hopital's rule. But if you're given indeterminate limits, and there's more than one way of solving it, obviously there are, but if you could use L'Hopital's to get the answer right away, why not use L'Hopital's? Okay, so L'Hopital's is a very nice result as long as it's nice and easy. And L'Hopital's isn't always the most convenient way of approaching these indeterminate limits, but it's a nice way of quickly trying to find an indeterminate limit. Okay, so that basically takes care of this section.